All right, welcome everyone. Good morning, good afternoon, good evening, wherever you are. My name is Lindsay Florence, and I'm an associate scientist here at Pumas AI. And I'm joined by Jose Storopoli and Patrick Mogensen of Pumas AI as well, who are going to teach you today about censored and truncated data models in Pumas. Next slide, please. If you're not familiar with us at Pumas AI, we are here to support scientists, engineers, and whoever else from discovery to delivery. We have two main products, Pumas, which focuses on drug development modeling, and Live, which is a clinical decision software being used in hospitals. Next slide, please. Today, we're going to just focus on Pumas, which is our accelerated drug development software. It's one of the fastest in the market currently and focuses heavily on pharmacometric simulation and modeling. Next slide. And here are just a few Pumas modules. We have things like non-compartmental analysis, nonlinear mixed effects modeling, QSP, bioequivalence, and so on and so forth. Some things to point out, we are validated against other industry softwares. We are a one-stop shop, meaning that you can do your data wrangling, your modeling, and your reports within Pumas. We are accepted by the FDA for submissions. We are super fast, as I said, because we are using great computers. And then we also have some machine learning that we are integrating as well. Next slide. So with that, I will hand this over to Patrick to teach you a little bit more.
Thank you, Lindsay. My name is Patrick, and I'm a director of research engineering at Pumas, and I mostly spend my time developing and the Pumas software itself and making sure that we get new releases out to our users. Today, we will be talking about the missing data problems, and we are going to be talking about truncation and censoring, models with truncation and censoring. I will go a bit through the motivation, what kinds of situations might we want to use this in, and where is it necessary, very little bit about the statistics of it, and some examples of where this was actually requested by regulatory bodies as part of a submission process. Then I will briefly talk about how you can do diagnostics in these types of models, but Jose will show you a lot more about that in the demonstration. Then I will show you very briefly how you do it in Pumas, how you use these kinds of methods, and sort of why we designed it the way we did. And then there is a live demo that will take up the rest of the time. Okay. So to sort of set the stage, when we're working with truncated and censored model in a missing data context, we have some variable that we call x here on this slide. That is the quantity that we want to measure. Okay, so we measure it using some instrument, and in our data set, in the end, we get a variable that's either yt or yc here. The first situation we can have where we have some missing data is the truncated setting. The truncated setting is where we measured the object of interest x, and we got a measurement back. But for some reason, if the measurement happened to be, or if the value happened to be below a, the lower limit of truncation, or above b, the upper limit of truncation, we don't get that data. We don't even see it. So that could be a situation where we, as the modelers or analysts or people who are reviewing some other study, we get the data after it has been cleaned, and for some reason the data cleaning process removed the observations, for example, if they were below the lower limit of quantification. It could also be that some limits are not, you're not allowed to see them if they're outside of some interval, for sort of, you might be able to identify people, but in this case, it's more often the case that you just got some clean data and you don't know if there were any measurements that happened to sort of be below or above the truncation limits. Okay, so that's kind of important that once measured, if it was outside of this interval, we don't see the data. We don't even know if there was an observation or not. the censoring case is different. We still want to measure our x variable here, but if the value happens to be below a lower limit of quantification or above an upper limit of quantification, we either just have a column that indicates that this was the case, or we just have that value in our data set. For example, if it's 5 milligram per liter, then we get the 5 in our data set, and we will then, in our material that is sort of that we get with the data, we can see that, okay, the lower limit of quantification was 5, so all these values at 5 are the censored data points, right? So actually the variable was maybe 1, but since our instrument can't accurately measure levels below 5, we just get that censored value of 5 if it's the lower. Yeah, okay, so just reiterating here, with truncation, we never see the data if it was outside of the interval, but we still know the limits where that would happen, which is important for the statistical theory. And censoring is the case where we actually know that we know all the measurements where they were when they were taken, but if they were below or some lower limit of quantification, we don't see the actual value. We just know that there was a measurement and it was below or at this limit. Okay, so that leads to two different statistical sort of models. So it's important to sort of know how to distinguish between these two. Okay, so the history of these methods go way back to the beginning of what we might know as modern statistics, with Fisher, who was one of the grandfathers of the statistics that we use, and was later developed by other authors. We of course like to mention that the maximum likelihood estimate, the maximum likelihood analysis of these type of models was published in 49 by a Danish statistician, Hal. But there have been many different treatments of it. Tobin a bit later, who had also a continuous measurement, like our concentration curves, for example, and then a probability of actually observing the value or not. So that's censoring that case. In pharmacometrics, the methods have been used for longer, further back than 2001, when Beal put out this paper at the bottom. But there was a bit of a confusion about what methods should we use, and is it important? What kind of bias can we expect? And I think there were some sort of news groups, so mailing lists, where some people asked these questions, and Beal sort of took it upon himself to write a paper comparing all these different methods. And this is the paper where all the M1, 2, 3, 4, 5, 6, 7 some sort of terminology comes from. So for example, the censored data case that we talked about before is the M3 method. But in Pumas, as you will see, we like to call it by the statistical names. But yeah, this is where that comes from. You've probably seen it before, M3, M4, M2. So yeah, so now it's part of, I would say, if not all, then most pharmacometric software, and that is because, as you will see, it's sometimes needed to actually include this statistical property in your modeling to satisfy regulatory bodies, or just to get unbiased estimates. So if you've attended some of the previous webinars, you will know that in Pumas we of course allow for different kinds of likelihood approximation methods, and there was a 1 or 2 webinars about the FOCE method and how it can be used in conjunction with different dependent variable distributions, but also how we can use different random effects distributions. Unfortunately, we can't use FOCE in this case when we have censored or truncated data. We have to use the Laplace I method when we have this missing data problem. And I say unfortunately because it is something that you have to keep in mind when you're doing your analysis, that it does come at a significant computational cost to use Laplace I over FOCE. On the other hand, if it's important in your case that you use this censoring information, then of course there's no way around it unless you can sort of convince FDA or EMA that they have to sort of let you do it without it. So you have to do it because it will cause bias if you don't, but it does come at a computational cost. Just something to keep in mind. So is it relevant? Well, as I already sort of alluded to, it can be very relevant. So maybe you're in an academic setting and you're very worried about bias in your estimates and you're looking for some ground truth. Then of course it is relevant to handle it, but it's also relevant in practice, because if you have, for example, data that's below some lower limit of quantification and you submit your analysis to the FDA, for example, then they might, without censoring information being handled explicitly in the statistical model, then they might come back and say that, okay, we want to see the analysis redone with censoring information included. So of course it's important that Pumas can handle these methods, these statistical models, and we do. So I just have a few examples. One example of a study that related to the safety of moxidectin in this onchocerciasis thing. It's a specific kind of nematode that you can find in a lot of developing countries, and it is actually one of the largest causes of blindness in the world. So of course this is a very important thing to study. And as you can see in the actual the FDA, when reviewing this application, they said that we actually want you to use the M3 method, which is including the censoring information in your analysis, because they were worried that there was too large of a fraction of the data set that actually had data below the lower limit of quantification. And so, you know, if you want to do it in Pumas, we will show you how to do it today. But that's one example where the FDA asked for this to be done. And I found another example in a short bowel syndrome situation in pediatrics, where the EMA also asked for, it's called BLQ here, right? But censoring information to be included in the analysis, because they were again worried that there was too much data that was down there. And we know that if we don't include that information in our statistical analysis, we might get biased results. So of course we want to get this right. Yeah, so that's just two examples, and there are many more. These are both M3 related. I did a sort of review, and it was a bit hard to find anyone using the M4 method, for example. But M3 is often used, and as I said in the beginning, we like to call it something else than M3, and this is called the censoring. So you will see the censored type of distributions later on. That's M3. Very important. Okay, so when you're doing diagnostics, you often look at weighted residuals. But the problem when you have truncation or censoring is that it's not really applicable, because the weighted residuals really rely on having that normal distribution for your dependent variables. And while the X, the thing that we want to measure, that we're fine that we're fine by assuming that it has a normal distribution. The problem is that the thing we actually observed, the censored or the truncated variable, that is no longer Gaussian or normally distributed. And so the theory for the weighted residual sort of breaks down. An alternative that is also popular in other situations is NPDEs. Truncation, we don't really handle NPDEs for truncated models. It's a bit complicated conceptually, so we don't have that. But I would say that it's much more often the censored case that you want to consider, and we do handle NPDEs for those. So the paper at the bottom describes how to implement it, and we've implemented it like that. So So you can use NPDs to assess the quality of your model in Pumas. There's also VPCs, or visual predictive checks. In the truncated situation here, it's very simple. You can just simulate directly from it. For all the measured concentrations that you have, for example, if it's concentrations, you can simulate a value. In this case, it's a bit more difficult for censoring because if you compare the VPC just with the lower limit of quantification substituted for the measurement, you will get some very weird looking VPCs. Luckily, there were some papers that described how to handle that, and we can simulate what let's say it's a concentration, we can simulate it if it was censored, and then we can impute some data and use that to draw some VPCs. It has a lot of drawbacks, but it is something that you can do, and we do support it in Pumas. Okay, so as I said earlier, in Pumas, we generally like to keep the naming and sort of the way that you write things very close to the math of it or the statistics of it. And the same thing goes for these missing data models. So for example, if you have truncated data, that is, if your measurement was outside of some interval, you don't observe it, but you know that you wouldn't have observed it if it was outside of those intervals. Then you can wrap your dependent variable distribution, that's a normal distribution here, you can wrap it in a truncated wrapper with the lower and upper limit, and then we will add the appropriate terms to the log likelihood contributions when doing the fitting. And the same is true for censoring. You add the censored around the normal distribution, and then you add your lower and upper levels, and those can be, for example, 5 as in the example I gave earlier, and infinity for the upper limit. And in that case, there's effectively only a lower limit. And as I said, you have to use Laplace I, you cannot use FOCE. So you fit the model using model population parameters, initial parameters, and specify the Laplace I. But Jose will show this in much more detail in the live demonstration. It's just to say that our philosophy is to call things by their name here. So, this would be M3, for example, but we just handle it directly in the derived block that is used to specify the statistical model. So that was it for me. I hope you sort of saw that what it is if you weren't aware or were reminded, and also realized that it is something that you can be asked to do. So it is relevant to know how to do it in Pumas if you are a Pumas user. So now I will
back to me.
To Jose.
Yeah.
And I guess stop sharing so you can share your screen.
Yeah. We'll take questions at the end. So I will start sharing my screen. I think it's this one. And one thing that Lindsay forgot to mention, but I mention now, is that Pumas is free to use for academic purpose and teaching purpose, research in academia. If you are not an academic, if you are in industry, please contact us at sales@pumas.ai, and we are happy to demo more things or go into a deep dive in whatever Pumas topic or PK topic you want us for dive to. So I think everyone is seeing my screen. This is a Pumas IDE running in the cloud. I have a data set called top.csv, which is a classical one. It's used in a lot of demos in other softwares, and also in Pumas we use that data set before in other webinars. So I'm going to hide this to have more room here to show the code. I'm loading a couple packages, Pumas, of course. I'm loading also Pumas utilities to have a function that compares estimates. So that function lives inside the Pumas utility. I need to read a CSV file. I want also to showcase something. So I need a simple optimizer from optmin.jl. Also, I'm handling data. I'm doing a data wrangling. So I need data from Smeta. And I'm doing plotting. And I need also AOG with the Cairo Mackie backend. And one more thing I am using to showcase different distributions, censored, truncated, and vanilla one, a regular one. I'm using the ECDF function from the stats-based package, which is the empirical cumulative distribution function. And let me showcase something before we dive into PK models. So I have a variable x. I'm saying that x is a canonical normal or a standard normal, which has mean 0 and standard deviation of 1. I wrap that, as Patrick showed, in a truncated. I'm specifying the lower bound as 1, -1, and the upper bound as infinity. So no upper bound, it's just lower truncation. So this is xt for x truncated. And I'm doing the same with the censored, with the lower bound as infinity, the lower bound is -1 and the upper bound is infinity. So a lower censored variable. I'm going to draw some samples, setting a sample size to n. So I have a random from my normal, no truncation, no censoring. It's x baseline. I have also the x truncated. I have also the x censored, and the x censored, I cannot do random on xc because we do not support you generating random samples from a censored variable because it's undefined behavior in our point of view. So we don't know what the user wants. So we, in our discussions, we do not support that. We took the decision of not supporting. So pretty much getting the max, either of -1 or whatever is sample from the standard normal distribution. So this is pretty much a censored, because anything that goes below -1 will have automatically the value -1. This is the difference between truncated and censoring. And I'm going to create some histograms to show you. So I have a AOG layer, which is the baseline. It's just data using the truncated. I have the layer truncated, the layer censored, and I have a histogram layer. If I combine those and I draw the first layer, so this is our normal distribution histogram. As you see, it's the familiar bell-shaped distribution. If we do the truncate, you see that it still resembles the bell-shaped distribution, but we have a truncation at -1. Now, if you do the censored, you can see that it doesn't resemble the bell-shaped because anything below -1 automatically got assigned the value -1. So that's the difference between truncated and censored. In practice, this is what you see in a truncation versus in a censoring context. So let me show some empirical CDFs. So this is more easily to view also. I'm creating just the range. I'm going to go from -4 to 4, and the length is 1,000. So that's our range. And I'm going to draw several empirical CDFs here. So the first one is the normal. So this is pretty much what everyone knows from the CDF of the normal. So we get our median is 0, and the mean is 0, the mode is also 0, and this is our normal empirical CDF. It's a monotonic increasing function, like all CDFs. Now let's show the truncated one. As you can see, we do not have any mass below the truncation point and at the truncation point. So all of the mass begins at -1, and then the curve is a little bit more steep. So as we can see, our median is actually far from 0 and not 0, and also the mean is also not 0. And let me show now the censored. So the censored, we don't have any mass below the censoring lower limit, but we do have considerable mass at the censoring lower limit. So this is the difference. And here you see that 10% of our observations, they happen at the lower censoring truncation. So this is what you see in a censoring, or the difference between a censoring normal and a truncation in your random variable. It's expressed. It has different histograms and densities, and also different empirical cumulative distribution functions, ECDFs. And if you take the mean of both of those variables, let me close this for now, you'll see that we have a bias in the truncated and in the censored. So in the truncation, we have a lower bias because all of the values below the truncation, they are pretty much eliminated. And in the censoring, all the values below the truncation, they are or upper or above the truncation, they are assigned either the lower boundary or upper boundary by default. So the bias is still is slightly lower than the truncated one, but we cannot estimate the mean and the mean analytically with a closed form solution, but we can estimate both the mean and anything else numerically. So this is pretty much let me take out this zoom a little bit here. So yeah, we can see everything. So I'm pretty much estimating numerically using the log PDF, where the log PDF is maximized or the negative sum is maximized. So pretty much in both optimizations, in this optimization, I get back a minimizer which is pretty close to 0. And if I go into the censored, I also get a minimizer that is also close to 0. There you go. So we can estimate those numerically. You cannot estimate it analytically in a closed form solution like you can with like a mean or a standard deviation. You can pretty much estimate a mean of those of the censored and truncated variables numerically. That's what we do in our models. So that's basically the idea behind and some intuition behind those two different types of random variables, the truncated and the censored one. Now I'm going to go to the toy example. I'm reading the TOP model, and I'm simulating first the truncated. This is the truncated example. I'm simulating truncation. So I'm pretty much transforming my data set. Whenever my dependent variable is missing or is below 0, below 5, sorry, you set its value to missing, otherwise keep its value as the current one. So pretty much I'm not touching the missing, the original missing rows, which are dosing rows, because this is a non-man data set. And I'm not, and anything that has our dependent variable, our concentration below 5, I'm setting as missing. And I'm creating a population with the read Pumas function. I have two covariates, weight and sex, and this is my model. The only important thing in my model is pretty much here in the derived block that Patrick already spoken a little bit. So is this line here 106? In this line, I'm conditioning my likelihood to on my concentration to be a truncated normal with a lower bound as 5 and an upper bound of infinity. So pretty much only a lower bound truncation is going on here. So this is my model. I'm setting like a initial parameter estimates, and I'm fitting my model. And here is important that my fit, the optimization method that I have to use, the only one that works, is Laplace I, because I do not have a good approximation for the likelihood function for truncation or censoring inside the likelihood function. So pretty much FOCE, it's a no here, so I cannot use it. So I have to calculate numerically the Hessian in the Laplace I estimation method. So I fit this, and I don't know why it's giving me an error, but it wasn't giving error before. And here is the fit, just to show it for you. So this is the truncated. I don't know why it's erroring. So Murphy's law, it's a live demo, but this was my original fit. I ran this ahead, so that was supposed to have here. So these are my estimates. This is my log likelihood value. One thing to notice is that in the truncation, I'm adding missing values to my observations. So I have less data points than other models. So that's why I cannot compare truncation with censoring, because truncation, I'm removing observations, and censoring, I'm overriding the value of the observation either above the upper limit or below the lower limit. I'm changing that to the limit. So I'm not throwing out any data point, any observation at all. So I have more observations than a truncation. So that's why we cannot compare log likelihood functions and anything that use log likelihood values and anything that uses log likelihood as a model assessment. So AIC, ACAIC, information criteria, BIC, anything that uses log likelihood, we can pretty much throw out of the window because we cannot compare, because the log likelihood is not similar, is something that we cannot compare because truncation uses less data points than censoring. So let me showcase the censoring method. I read the data frame again, but now I'm pretty much setting a max. So our dependent variable, our concentration, is pretty much a max. And here I have to do a pass missing, I guess. So pretty much a maximum of 5 for the dependent variable. So anything below 5 is going to have the value 5. This is different because we are not creating any mission values. We are not throwing any observations here. And I read the population, the same thing that I do. My model is the same except for line 157, that now I'm adding a censoring in my likelihood function. So this is a censor normal where the lower limit is 5 and the upper limit is infinity. So no upper limit, only lower limit. And let me see if this fit will run, because yeah, it runs. So we get back our estimates. And if we take a look at the comparisons of the values, you see that a lot of parameters, the values are similar. Even the omegas and the error. But for theta 1, which is a parameter that was directly related to the concentration, we see different values from the truncate and the censored one. So you get different estimates for different models, the M3, which is the truncated, or the M4, which is the censored. And also, if we take a look at the visual predictive plots, we also get different VPCs for them. So it's running. 1 second. And as Patrick said, we can also do NPDs. Oh, there you go. So the first one that we generated is for the truncated. And as you can see, the VPC is very bad. And the last one 13 out of 13 is the censored one. And you can see that this VPC is much, much better a plot. So this is a much better fit if you go by the visual predictive checks. And also if you take a look at the NPDs, you can pretty much call inspect in your fits. And if you pass the inspect function, by default, it's going to calculate weighted residuals, empirical based estimates. And by default, since it's a little bit computationally heavy, we do not calculate any NPDs, but you can do so specifying the nsim keyword. Here I'm using 1,000 simulations to calculate my NPDs, my normalized distribution, predictive distribution errors. So I'm pretty much using 1,000 to calculate, but you can go more if you can say 10,000 or more. And I'm doing the same for the censored and truncated. And if you wrap this inspect, the return in a data frame, you see that we get a column here called DV, which is your dependent variable, your concentration, and you get your DV pred and IPRED, and you also get your DV weighted residuals, which also has some issues in the truncation and in the censoring. And you get also your DV NPD here for both of them. And now I'm plotting those. Here I'm doing a drop missing in the truncated one because we do have missings in the truncated one because we throw out observations. We set values as missing below the truncation point. And I'm doing a histogram, so I needed to drop missing in the DV and PDE column. And here is our histogram. So it kind of follows, this is for the truncation one. It kind of follows bell curve. So the errors are normally distributed. And if I do for the non-truncation, for the censored one, here it is. You see that the errors, they do have a slight bias. It doesn't resemble now, resemble now a bell curve. And I can also compare, I can also do a DV against DV NPDs in the X and Y axis, and I can add a linear trend and also do a scatter plot. And this is from the truncation one. And you can see that we have kind of a slope here. And we can do the same for the censoring here. And here in the censoring, you see that a lot of observations, they cluster around the lower censoring limit. And your slope is different because of the bias that we saw it before in the histogram. And also we'll get like more a bias for positive errors rather than negative errors. So this is pretty much how you inspect censoring or a truncation fit. And I will throw back to Patrick. He's going to showcase in 5 minutes one or two like real world examples. These are just toy examples. And I'm going to stop sharing my screen. And in the last 5 to 10 minutes, we'll take questions. I don't know if you're speaking, Patrick, but we cannot hear you. At least I cannot hear you. Let's wait like a couple more seconds for Patrick. Otherwise, we'll go to questions. No, we cannot hear you. At least I cannot hear Patrick. I don't know if I cannot see you also. I don't know if it's my Zoom or your Zoom. So can anyone hear Patrick, or you folks cannot also? We cannot hear. Okay, thank you, Lindsay. Yeah, Patrick, so if you want to try to rejoin us, feel free to do that. Yeah, he's rejoining us. No, great question. So I'm going to cover that while Patrick is rejoining. So there is a macro, there is a function called drop missing, and this function is for a data frame you are drop missing. And there is a macro in data frames meta which is called pass missing, has the at symbol, which denotes that is a macro. And this pass missing, it's a function to tell to propagate missing. So when I'm doing like max 5.0 or dv, I want to make sure that this max function will propagate missings whenever it finds a missing value in the dv. So these are for dosing events in my data set. I'm pretty much confident that the max function propagates missing by default, but I don't want to risk it, so I pretty much do a pass missing for that. And Patrick is in the waiting room, and I need to admit him. So I don't know if that answer your question. Yeah, now we can hear something from you.
Okay, can you hear me?
Yeah,
Okay.
we just cannot see you, but we can hear you.
Okay, so that was a yeah, a long wait for nothing. I don't have anything further, Jose,
Okay.
but I can show my face. Yeah.
Okay.
Now all the technology is working again. No, yeah, that was it for the demo and for the presentation. So, yes.
Okay, let's go to questions. You participants, feel free to open your mics if you want to, or to type it in. Go ahead. We have 30 minutes for questions.
All right, if there are no more questions, feel free to always contact us at sales@pumas.ai.
Oh, hang on, we have a question. Yes, go ahead, Akusua.
Yeah, I just want to find out, I use an LMXR instead, and like the NMXR, the R package for, yeah. And in the data set, normally for the censored and non-censored data, we stratify them, like we give them some codes like 0 and 1 to allocate them. Is it the same thing with the Pumas AI in the how you set up the data set?
Do you have experience with LMME mixer in R, Patrick?
Oh,
Okay,
sorry.
so to answer the question, what you were saying that is that you have some kind of indicator variable that is one for the observation being censored or 0 for not being censored.
Exactly.
Yeah. So the way that it's set up in Pumas, and after this is over, you can review the example that Jose showed, is that you will the data, if you get it, it depends on how you the person who prepared the data did it, but the way that you have to do it for Pumas is that you will set the value of the observation to the, for example, lower limit of quantification, I guess 5 in the example in the live demo. It will be 5 in the actual data frame, or the data frame that you give to read Pumas. And then in the model, when you say that it's a censored normal with lower limit 5 and upper limit infinity, that will automatically detect that it's censored because it has that value, right? So the DV is the name for the observation in the data set. It's a column, and for all the censored variables, it should just have the value 5 in that row. Does that make sense?
Okay, I'll have a look at the data file and everything and see.
Okay.
If I have any issues, I'll just email. Yeah.
So I
think it makes sense. Yeah. Thank you.
It will just know that it was censored by matching the value.
Oh, okay.
That you have here 5, and the value that you have in your observation. So if your data set is in a way, for example, let's say you do actually get the values from the instrument. Let's say you got a value of 3, but you also know that that is below the limit of quantification, right? Then you would have to add a data step where you set that value to 5 instead. You can make a new column, call it DV censored, and replace all the values below 5 by the value 5, and then use that in your analysis.
Oh, okay. Okay. So if like I have a data set whereby like below limit of quantification is undetected, like nothing reads, is that why in that case, what happens? Like it's 0? It's undetected.
Yeah, so then you would still, if I understand you correctly, you would still have to set your observation to the lower limit of quantification, unless I might be misunderstanding your use case here, but
okay, because I deal with viral load data, and maybe some of the values are undetected below the instrument, like that. They are undetected values. Yeah.
Yes, but do you know that limit, or you don't know it?
Yeah, I know. Like for SARS-CoV-2, for instance, it's like CT value 40. Like it's 40. The CT value of 40. That's the limit of detection.
Then you would set it to 40 in your data set, but you don't have to override the original column. You can make a new column and then use the name of that column in your model.
Oh, okay. Okay, I get it.
Yeah, just so you keep that original information still in your data frame.
Okay, thank you.
And also, just now that we're talking about how to specify it, if you, for example, have measurements at different locations, right? So you might have different instruments taking the measurements. You can also have different. Could you go to the derived block, Jose? Just briefly. So if you, for example, have different instruments taking measurements at different locations, you can include that information as a covariate and use that covariate name instead of the 5.0. So that way you can have, in the same data set, you can have different levels for these censoring thresholds.
I have a data like that, so I think I'll have to have a look at this, because I have another data sets whereby there are different LODs, so I might have
to. So if it was 40 in one location, or for one instrument, and 80 for another, you could have that information there in the covariates.
Here, and then you add it here. Yeah. So this is a column to say, okay, this is a covariate column, and then you pretty much condition your censored likelihood, the lower bound, into that column from your original data set.
Yeah. So you would have to know what subject was measured using what instrument, but if you do have that information, you can include it like this.
Okay. All right. I just have to look at it. Thank you.
Yeah. You're welcome.
Yeah, I'm trying to stop sharing, but the button has just frozen me. Okay, I don't know how to stop sharing. The button is not working. Any more questions? Okay, stop sharing.
If there are no more questions, the webinar replay with the code and slides will be posted to Pumas Labs shortly later this week. We also have a webinar at the same time 2 weeks from now on SAEM in Pumas. If you would like to join us, please register for that as well, which will also be sent in the follow-up email with a number of other webinars and workshops we will be offering in the near future. If you have any questions, as always, you can contact us at sales@pumas.ai. Know that Pumas is free for academic and research purposes. However, if you are in industry at like a pharmaceutical company, you will need to contact us at sales@pumas.ai for a license. With that, we hope you have a great morning, afternoon, or evening where you are located. We'll stick around for 2 or 3 more minutes in case anyone else has any questions they don't want on the recording, but otherwise, please have a good day or evening.
Yeah, let me stop the recording. I never did that. Stop recording. Okay.